Wide field of view cameras are very advantageous for robotics applications. For example, in object segmentation and detection, we can detect more objects compared to perspective cameras. We can also track an object with wider range of movement without having to move or rotate the camera. It also adds robustness and accuracy for visual odometry and SLAM applications. In this work, we focus on the advantages of wide field of view cameras on depth estimation and 3D mapping. Wide field of view offers more geometric information in a single view compared to perspective view cameras. We can also simultaneously visualize and observe multiple objects in multiple directions. By having depth data in multiple directions, we can also improve navigation and path planning algorithms and make them more robust. In this research, our goal is to estimate a dense depth map that is both accurate and runs in real time using RGB images from wide field of view cameras. Several work have addressed the depth estimation problem. We can categorize them into sparse and dense methods. Sparse methods include state-of-the-art techniques such as semi-global matching and plane sweep. Gao in 2017 and Hein in 2014 applied these methods on fisheye cameras. Sparse methods are fast and can run in real time in CPU, but obviously lacks information, especially in low texture areas. On the other hand, dense methods have more information and are inherently smooth and have sub-pixel accuracy. Most dense methods are applied on perspective cameras such as Sumer in 2010 and RAMF in 2012. Recently, Schneider presented an evaluation of dense techniques using wide field of view cameras. Compared to sparse methods, dense methods are more time-consuming and mostly require modern GPUs for real-time processing. We also categorize recent work as either rectified or non-rectified depending on how they handle the distorted images from fisheye cameras. Rectified methods require converting fisheye images into either perspective or spherical projections, while the rectification allows straightforward adaptation of a long history of perspective methods. They suffer from reduced field of view and the resulting images have unwanted distortions and compressions to preserve straight lines. On the other hand, non-rectified methods work directly on the distorted fisheye images. Without rectification, the wide field of view is preserved. It also prevents subsampling of the images, which can degrade their quality. Hein in 2014 and Caruso in 2015 proposed depth estimation methods that can handle the distortion of fisheye images without rectification. This table generalizes existing work into these categories. Our proposed method called Variational Fisheye Stereo lies in the non-rectified and dense depth estimation category. We accumulate the advantages of both categories such as information density, smoothness, accuracy, and wide view and image quality preservation while addressing the shortcomings such as distortion with our epipolar curve estimation and time consumption with our real-time implementation. Our method requires a pair of fisheye images with known relative poses and calibration parameters. These images can come from a binocular stereo pair or a monocular sequence. Using the relative pose and calibration parameters, we calculate a trajectory field which we use for solving the image gradients. The gradients are used for the real-time variational stereo optimization, which requires minimizing an energy function, usually with a data term and a smoothness term, and outputs a dense disparity and later converted to a dense depth map. The optimization is embedded in an iterative framework employing a warping technique to handle large disparities. Our first contribution is a fast gradient calculation along the epipolar curves using a trajectory field. Second, we propose an accurate warping technique that relies on the trajectory field for correct estimated warping directions. Finally, our implementation of the iterative optimization is in real time. The first issue we need to address is the direction of the image gradients. In the energy function, the data term is a brightness constancy constraint that penalizes the difference between the texture of two images I1 and I0. This energy is linearized using the first-order Taylor expansion. The derivative term is a directional derivative that is dictated by the relative camera motion. In the perspective image, this direction is guided by the epipolar lines. This derivative is often discretized as the difference between two pixels with distance equal to the disparity along the epipolar line. Since the epipolar line is constant for an image pair, the directional derivative only needs to be solved once. On the other hand, fisheye cameras do not have epipolar lines but epipolar curves, and the direction of the derivative needs to be calculated in every iteration, which is a straightforward approach in solving this issue. To correctly estimate the direction of the epipolar curve in each iteration, We need to unproject a ray from the first camera, crossing a pixel to an arbitrary surface, and then reproject the second camera. The pixel of intersection then indicates the estimated direction of the epipolar curve. We need to do this for every iteration in every pixel until we reach an optimum disparity. The problem is that the unprojection of a ray is a non-linear process and requires time-consuming iterative solution itself to be accurate depending on the camera model. While some camera models have closed-form unprojection functions, real cameras can only be accurately modeled using a nonlinear distortion model of which, as of this moment, has no closed-form unprojection. Hence, our proposed solution. In a similar manner as the baseline approach, we unproject and reproject a ray from one camera to the other. The vector defining the different intersection in the image plane is used to define the trajectory field image. However, instead of performing this for every iteration, we only estimate the trajectory field once for every image pair. We then use a straightforward bicubic interpolation to solve the direction for successive iterations. By using this approach, we are able to use hardware acceleration for modern GPUs, which dramatically reduces the processing time. The second issue that we need to address is the warping direction. The warping technique incrementally brings pixels together and are often employed to handle large pixel displacement. In the perspective case, each iteration converges to the optimum disparity. The direction of the initial disparity is indicated by the direction of the epipolar line. At the optimum solution, the final warping vector is equivalent to the total disparity. This is not the case with fisheye images. The direction of the incremental disparity changes in every iteration, and therefore the correct warping vector also changes direction. Moreover, the length of the total disparity is different from the length of the warping vector. To get the correct warping vector in every iteration, we only need to sum the incremental disparities with their direction. The direction is again indicated by the subpixel direction solved from the trajectory field. Using this approach, however, needs to be controlled. If we don't limit the length of the incremental disparities, we will end up tracking the wrong epipolar curve, which will degrade the accuracy of the depth estimation. We solve this problem by applying a simple thresholding of the incremental disparities for every iteration. Finally, we use a state-of-the-art energy function called Total Generalized Variation L1 or TGV-L1. This function consists of a data term and an image-guided edge-preserving smoothness term. Using this function allows us to produce smooth surfaces as well as maintain sharp object boundaries. We evaluated our method on different datasets, including a synthetic dataset with 300 sequential frames and 4 stereo pairs rendered from Blender 3D, and a real dataset created from a 3D laser scanner with 144 image pairs and arbitrary camera motion. We first evaluate the importance of limiting the magnitude of the incremental disparity. In these images, we can see that the photometric error increases when the incremental disparity is large, especially in high texture regions such as object boundaries. Moreover, the plot shows the accuracy decreases as the incremental disparity limit increases. We also compare our trajectory field generation and sampling approach with actually solving the epipolar curve per iteration. We compared with different camera models and different unprojection functions. As expected, models that don't have closed-form unprojection functions such as the unified camera model with distortion model and the Canala-Brandt model greatly increases the processing time. In all the methods, our trajectory field sampling approach is the fastest. We compare our method with non-rectified sparse method by Hain. In all the dataset, we achieved complete depth density with lower error in both the erroneous pixel measure and the mean absolute error. Here are more qualitative results of our method. We also implemented our method using a commercial off-the-shelf fisheye stereo camera called RealSense T265 by Intel. In this video, we show the results of our real-time implementation and compare the results with the sparse method by Hain. In conclusion, we propose a variational fisheye stereo method that is accurate, dense, and runs in real time. We also simplified epipolar curve estimation using trajectory field and bilinear sampling. We also propose a warping technique to handle the fisheye distortion and produce the accurate depth map.